Well, hey, Math 8, Mr. Erickson here. Welcome to this week of e-learning. I'm just going to shoot a quick video here from Monday just to kind of go over this lesson a little bit, as well as just kind of let you know what's coming up this week. So this will be, today's here on Monday will be lesson 10, which is the last lesson here for unit 10. So on Wednesday, we're going to do a review assignment. It'll be lessons 5 through 10. So not the whole unit. I know that would be a lot of stuff. So it's just the second half. So just basically unit lesson 5 to lesson 10. And then on Friday, you're going to take a quiz here on Canvas that would go over, once again, just the second half of the unit. So this is our last lesson here, lesson 10, which goes over mutually exclusive versus non-mutually exclusive events. And so I just thought I'd kind of scroll through this a little bit, talk over the notes here. Let me know if this is helpful. I'd read the surveys just saying maybe more videos, less reading, and so I thought I would give this a try. Yeah, let me know what you think. If it's the kind of video you'd like, or if you'd want one that would go over a PowerPoint or something like that. That might be a lot of work on my part, but if that would be helpful, we could maybe do something like that. So let me just kind of talk over this. So if last week, I know we kind of basically really focused a lot on basically independent versus dependent events. Okay, so that was last week. So we had independent versus dependent. Now, just to really quick kind of go over that and talk about how that's different from what we're doing today. So first of all, of course, independent means that you were doing two events, and so the first thing would not at all affect the second thing. So a great example of this would be is if you had like a deck of cards, right? So you shuffle up the cards, you pull a random card and say, hey, what is it? Maybe it's a queen of spades or whatever. So you pull a card out. Now, independent says, okay, whatever card you pulled out, put it back into the stack, you replace it, and then you reshuffle it up. And so the probabilities of drawing are the exact same the second time as they were the first time. Now, dependent, if you think about the word dependent, it means it depends on what happened the first time. So let's say it's a deck of cards once again, and let's say you pull out that queen of spades, and now you reshuffle up the rest of the deck, but you didn't put that that queen of spades back in, right? So now instead of 52 cards, I don't know how much you know about cards, deck of cards, but typically there's 52 cards. Instead of 52 cards, there's only 51 cards. Now, it might seem like a small change, but that automatically changes and affects a little bit the probability of now maybe drawing a second card when you didn't put that first card back in. Another great example of dependent events would be, I think we use this on the assignment, but would be like a package of M&Ms, right? Maybe you got a new package of M&Ms, you open it up, it's all shuffled, of course, and you want to know what's the probability of just kind of blindly reaching your hand in and randomly grabbing a red M&M. And so let's say you do that, you pull out a red M&M, you eat it, right? If you're eating that M&M, you're not going to put that M&M back into the package, right? That'd be gross. So you're not going to do that. And so that means that if you now go for a second M&M, once again, less M&Ms in the bag. And if you're maybe wanting another red M&M, there's even one less red M&M in the bag. So that's kind of the difference of independent versus dependent, right? Did you replace that first thing that you took out? If you didn't, then the probabilities change. It depends on what you took out at first. But if you do replace it, it'd be independent, where you shuffle it back up, it's back to square one, right? Blank slate, probability would be the same the second time as it was the first time. No harm done. So that's kind of the difference here. So now we get into what we're doing today, which is now switching gears to what we call mutually exclusive versus non-mutually exclusive events. And so let's just kind of talk over some of the notes here. So sometimes, once again, you're finding the probability of a single event, but you have the option of one event or another. So sometimes these events are exclusive, as in there's no overlap. That would be what exclusive means. But sometimes there is overlap between the events. Okay, so that brings us to kind of our main point here. So the first one here would be mutually exclusive events. Those would be events that can't happen at the same time. So there's no overlap. Once again, they cannot happen at the same time. And so an example of that would be, this is just a really easy one, but flipping a coin, right? On one flip, last time I checked, you're not going to get heads and tails. Now, I've taught this before, right? If we were in the classroom, someone's going to raise their hand and say, well, maybe it lands in the middle, right? I think there's a couple movies where that happens, right? You flip a coin, it just lands just right on the edge, right? It doesn't fall to either side. That really doesn't happen a whole lot. So we're going to say, once again, that's the very rare extreme case. So in that case, right, if it lands heads, it didn't land tails, right? If it lands tails, it didn't land heads, right? You can't have it land on both heads and tails at the same time. It's either one or the other. Okay, so that's an example of what we call mutually exclusive. That would be the term, mutually exclusive events. Okay, so when you're doing that, here's kind of the formula you're going to use, is that given two events that cannot occur at the same time, once again, they're mutually exclusive, what you can do is basically just add the probabilities together. So to find the probability of A or B happening, if they're mutually exclusive, of course, you would do the probability of A, whatever fraction that is, plus the then fraction of the other one. Now remember, when you add fractions, what do you need? Common denominator. So you might have to start thinking along those lines here for what we're going to be doing on this assignment. But anyways, all right, and then so that was the first one. Okay, versus, that was mutually exclusive. Versus here, non-mutually exclusive would be events that could possibly happen at the same time. So there is some overlap between the events in this case. So maybe we go to a die here. You could roll a 2, or maybe rolling, here they say a prime number, for example. So obviously 2 is a prime number. So there's some overlap there. Maybe a similar example would be like, say, rolling a 2 on a 6-sided die, or rolling an even number, right? We know 2 is an even number, but there's also some other even numbers, but there's some overlap there, right? It's not that you can't have them happening at the same time. Another example is just be kind of an everyday example that's pretty good, but picking a student that plays basketball or football, right? You guys probably know, some of you guys, you play both basketball and football, right? So it's not always that if you pick a random student, that they play only one or the other. Obviously, some of you guys are multi-sport athletes, right? So that would not be mutually exclusive. We would say that's non-mutually exclusive, where it's possible for you to do both. So, all right, so that's kind of the general idea there. Now, the formula does change a little bit when you're looking at non-mutually exclusive. So given that there's two events that have some overlap, what you need to do is, the first part's the same. You're still going to add the probability of each event, kind of like we did in the first one, but you got to remember to then subtract any overlap. Okay, so however many times there was that overlap, you have to subtract that away and kind of factor that in. So once again, you would add the probabilities here, probability of A plus probability of B, but notice minus the probability of where they both overlap, where they're both happening at the same time. So let's maybe look at just a couple quick examples here, and I may not do all of these, but just here as we close. So example 1, first we have to determine, is it mutually exclusive or not, and then we'll find the probability. So probability 1 here, picking a cube or a cylinder. So the question would be can you have something that's both a cube and a cylinder at the same time? Well, last time I checked, it's either a cube or it's a cylinder. It's not going to be, there's no cube cylinder or cylinder, whatever. Yeah, so you can't have both at the same time, right? So in this case here, we would say they are mutually exclusive, right? There's no overlap. You're either a cube or you're a cylinder. Okay, so now let's think of the probability here. So the probability of being a cube looks like, if we look up here, there's 1, 2 that are cubes. So we put the 2 right there, and there's a total of 1, 2, 3, 4, 5, 6, 7 shapes. So you put the 7 on the bottom. So 2 over 7 would be the probability of randomly picking a cube. Probability of randomly picking a cylinder here. If you notice here, there's also 2 cylinders. There's 2 of those out of course, the 7 total. And so you would then, if you wanted to find, and this is kind of what they're trying to get you to calculate here for your final answer, the probability of picking a cube or a cylinder at random, so it could be either one, you would just add the 2 together. So 2 out of 7 are cubes, 2 out of 7 are cylinders, add them together. Of course, already got that common denominator there. You get 4 out of 7, and that would be your final answer. Okay. Now, how about probability 2 here says, pick a solid, though, that is shaded or has vertices. So if you look up there, the shaded ones, of course, would be actually what I have circled currently, because those spheres that are kind of, white there, we're saying that's not shaded. So the ones that are shaded here would be the cylinder here and there, and then the cube there and there. Now, some of the ones that are shaded, being those 2 cubes, notice they have vertices, right? They have those different corners, the sharp edges and corners there on the shape. So it's possible for them to be both shaded and have vertices. So we would say that's not mutually exclusive, an example of that, okay, because the cube, once again, is shaded and has vertices, so there's overlap. Okay, so once again, we're going to figure out the probability of each, but we have to make sure we factor in that overlap. We have to subtract that away before we say, hey, there's our final answer. So probability of shaded, once again, 4 out of 7 here would be shaded. And then the cube, there's, once again, we had the same as above, 2 out of 7. are the cube there. So, but because we have some that are both shaded and a cube, we have to say, well, how many would that mean? So because there's two of those, right? Because both of the cubes here are shaded and have vertices, it'd be those are the two that are overlapping, right? Where it's both of them. Notice here we have our 4 over 7 plus 2 over 7, but notice we subtract away the 2 over 7. So we end up with 2 over 7 again. All right, so that's kind of walking through one example. I could take some more time and do the others, but you can also read through these as well just to see some more examples of kind of the same idea. So let me know if this is helpful. Otherwise, don't hesitate to reach out during office hours, either email or hop on Zoom. Remember, the link is on the Canvas homepage for Zoom. Also, remember, midweek feedback video will be coming about probably Wednesday or Thursday, especially with the quiz coming up. I might try and get that done maybe Wednesday or Thursday. That way you guys could watch that, get some feedback, how you're doing on the quiz and on this assignment before you take, or for the review, get some feedback on the review and this assignment before you would then take the quiz on Friday. So be looking on the Canvas homepage for that midweek feedback video. I'll go over some of the hardest problems as well as kind of re-explain just the basic ideas. Otherwise, I hope you guys have a great week. Miss seeing you. I know it's been weird not being at school, but I hope you guys are doing well. And as always, don't hesitate to reach out either for math help or even just hop on Zoom just to talk. I'm there. Love to talk to you. Otherwise, hope you guys have a great week and we'll talk to you later.